Okay, we're live.
Hi, everybody. This is Alex from the Astroimaging channel. Welcome back for the Sunday evening's presentation. We're going to go comet hunting. We're all going to get together and we're going to go look for comets. And we're going to keep track of every single comet up there. And we've got some people who are experts at this, some people who've been studying comets for a long time, some people who are just beginning to study comets. But we're going to show you how you too can rig your house so that you can be a comet hunter. Before we do that, I wanted to share a few things with you. I've been through, I don't know, 5 or 6 of these meetings of late, and every one of them operates a little bit differently, and it's always hard to figure out just which of these we want to be looking at. I want to take you first to the Astroimaging channel home, and we don't have a whole lot of stuff here, but it is some place with some important things about it. One is you can get to see some of our past shows by looking here, and you can find out some of our past shows. Of course, the main place is the YouTube channel, and we'll take you over there in a little bit. You can get a contact here. This contact is really good for giving us suggestions as to how to run the program and things like that. We do need some help running this program. We need some technical help, some people that know how to work Streamlabs or some other OBS programs. We need volunteers to be presenters. We need all sorts of help like that. So you can use this contact form to tell us some of that. On the calendar, you can see what the shows are coming up. Denis, Vida, and Bob Massey are going to be the main presenters today, but Peter Eschman and Steve Welch are all going to also come along and tell us about their comet hunting experience. And then over the next few weeks, we've got a whole lot of cool people coming in to tell us stuff. Manny Lines has been building an observatory up in Northern California for a couple of years now, and we've talked him into coming on and telling us a little bit about how he built his observatory up there, some of the mistakes he made, some of the good things, and we'll enjoy that. And then a week after that, Bob Zellam's coming over here from Caltech. He's going to be telling us about how we can use our pretty picture equipment to take pictures of exoplanets. We can go hunt exoplanet hunting. Bob Traub is going to be telling us about the PIX-Insight comet processing because we've got another comet coming up. Swan's coming up pretty soon, and hopefully it'll be bigger than Mars was when Mars was bigger than the full moon, if you can remember that. Richard Wright's coming back, Dale Gaunt, Sebastian Garcia from Telescopius, and Isa Mohammed is going to be telling us about electronic assisted astronomy. And in July, we've got some open dates, so we need volunteers. One other thing I want to remind you of is that I got to turn off my mic. There we go. We've got a comment section over here, and we are monitoring that comment section so that you can ask questions, both of the people hunting comments, and it looks like you guys swap stories among yourselves and things like that. So go ahead and ask your questions over there. Keep them on topic if you can, but if you got other things to say, go ahead. And if you have some other questions, that's okay too. Also, we've got a couple of important buttons down here. Oops, I've got too much stuff here. You can see how many subscribers we've got. We've got about 8,500 right now, and we're looking to get to 10,000. We've increased that by about 1,000 over the last year, and we'd like to have more. So it's important for you to go ahead and subscribe. You can make a donation. We always like the donations, and it does cost us to, have all these programs that we have to put together and pay for the website and things. So if you can do that, we'd appreciate it. But mostly, we're here to talk about astroimaging, and in particular, we're going to be talking to Denis, Vida, Bob Massey tonight. Peter Eschman, Steve Welch are going to be joining us, and it's about time to start comet hunting. So, Denis, are you ready to go start sharing your screen and take over?
Sounds good.
Okay, go for it.
Okay, let me click present. So, screen 2. Just a small correction, Alex. It's meteors, not comets.
I'm sorry. I was hanging on comments for the next.
I can understand that.
And a couple of others.
Okay. Can you guys see this?
Yes.
Yes, you're good, and you're coming through loud and clear.
That's great. So about 10 years ago, I was just an amateur astronomer interested in meteors, very keen, and I didn't really know much about the topic. It was just a few of us guys at the Croatian Meteor Network were really keen and keen in deploying cameras, keen in recording meteors, trying to do some citizen science. But from my perspective right now, we were missing a lot of background knowledge about the basics. So after that, I went on to do a degree in computer science. And after I finished that, I realized that I want to pursue perhaps a career in astronomy. And I decided to do a PhD in meteors. And I defended my PhD about 2 weeks ago. So I'm here to basically tell you what I wanted someone to tell me about 10 years ago. And why do we even deploy these meteor cameras, and why does the whole thing even matter? And the way I structure this talk is I'm going to talk about some things that we know, but also about some things that we do not know. What are the open questions? Because there's so many things. So first, I would just like to start off with some basic terms. So I understand that some terms can be confusing. What's a meteor? What's an asteroid? What's a meteorite? People get confused, and I can understand why, because all these terms are very similar. But a meteoroid is an object usually from a few micrometers to several meters in size that travels through interplanetary space. When that object intersects with the Earth, enters the Earth's atmosphere, it causes the meteor. Or if the meteoroid is big enough, it causes a fireball. So a fireball is just a very bright meteor. And the meteor is not the rock itself. It's just the light, the sound, the phenomenon that it produces. And if a fireball or the initial meteoroid is big enough and slow enough, it can leave a meteorite. That's basically that rock underground that you find. So where do meteoroids come from? Well, comets usually reside. So comets are these big bodies, sometimes kilometers in size, that are just basically these dirty ice balls are called, or icy dirt balls. Actually, the dust to ratio is actually higher than about 0.5. So they usually reside in the outer solar system, and they're yanked into the inner solar system by a big planet, let's say Jupiter, coming close, and they are ejected into the inner solar system. They heat up and they start releasing gas. So basically, carbon monoxide, carbon dioxide, and water ice that are trapped in below the comet's surface. They start sublimating, and they take these dust particles off the surface and eject them around the comet. And what you have then is, I hope you can see this video, these dust particles travel very close to the comet's orbit, but they interact with other planets, and there are also some non-gravitational forces. They just kind of deform this dust trail, what we actually call a meteoroid stream. As you can see, as this dust trail gets older, it gets more deformed. So here you could actually see a close encounter with Jupiter that caused this very complex meteoroid stream. So as you can see, younger meteoroid streams, so younger, it means more recently ejected, it's very compact right behind the comet's orbit. But then as it gets older, it gets more complex. And when this intersects the Earth's atmosphere, we can perceive that as a meteor shower. So basically just a bunch of meteors coming from this one part in this country called the radiant. And this is just a perspective effect. So, if you're here on the ground looking at here, you'll just see as if all these meteors are coming from the same point of the sky. But in fact, most of these trajectories are parallel or close to parallel. So what happens then is when meteoroids enter the atmosphere, they collide with air molecules. So an average meteor that you see is caused by about a millimeter-sized particle. So people get surprised because they think, oh, it's got to be something much bigger, but it actually isn't. It's like a grain of sand. And what happens is then it comes to the air molecules, the surface heats up, and the surface starts to vaporize. And this process is called ablation. So basically just this mass is removed from its surface. What we also observe with meteoroids is continuous fragmentation. These kind of small grains get released from a comet's surface and they ablate separately. And sometimes meteors can fragment. And you can actually notice that in the light curve, just there's kind of like a little burst. of light. And finally, they mostly completely ablate away. So the meteor phenomenon itself causes a big plasma tail or plasma trail around the meteoroid. So what happens is it just basically ionizes the air around it. So because the air is ionized, it acts like a big wire in the sky. So that's why some people are doing radio meteors, because you can bounce off radio waves of these ionized trails. They also emit visible light. We know they emit in infrared, and there's some indications that they might emit some signals and some electromagnetic radiation in ultra low frequency spectrum. If the meteor is large enough, there's also a bow shock, but that's only for bigger fireballs. It's interesting, though, that meteors, in theory, should be also seen on Mars, and possibly on Venus, because they have an atmosphere that is dense enough. Although, as far as I'm aware, there doesn't seem to exist one certain detection of a meteor on another planet except Earth. At least not from ground-based cameras. We have some images which could be meteors. So a meteoroid environment around the Earth is reasonably well known, but on other planets, if you want to model, what's the meteoroid environment there, we just kind of have to extrapolate from what we have at Earth. So where do these objects fall in the grand scheme of things? So here on this graph, you can see the logarithm of mass. And on this graph here, you can see the size. So meteoroids actually cover a big range of sizes, from about several micrometers to about a meter, several meters in size. So asteroids and comets are about here. And of course, you have, planets and the sun, other stars, et cetera, on this part. And on the other side, you have atoms and molecules. So meteoroids are basically in between the micro and the macro world. In our universe. And because this graph is pretty old, I mean, from about 98, I think, there was this one unknown area, what's between meteoroids and asteroids and comets. Well, in the last couple of years, we actually started discovering asteroids in the 1 meter size range. So we actually know that there is actually a continuous this size distribution. The problem is that asteroids are discovered by these big telescopes. They're trying to discover them before they enter the atmosphere. And meteoroids, well, we see when they enter the atmosphere and observe them as meteors or fireballs. When these meteorites are big enough, as I said before, they produce a meteorite. In this case, this meteorite went through a 1980 red Chevy Malibu, which is kind of famous. And also, we find meteorites on other planets. For example, on Mars, I think the rovers on Mars found several meteorites, and meteorites are an opportunity to study the bodies in the solar system without actually sending a spacecraft and recovering it and bringing it back. You just kind of wait until one falls and you collect it. So that's basically one of the reasons why we deploy these meteor cameras, is because if you have a rock and you observe the fall, you know where it came from. You don't have to send a spacecraft to collect the samples. So, it's all nice, but why should I really care about any of this stuff? Well, every once in a while, something like this can happen. So this was in 2013. Some of you might remember the big Russian fireball made all the news. And what was interesting, that it produced a very bright flash, and it also produced a very big explosion when the air blast reached the populated area, blowing up a lot of windows, injured a bunch of people. Actually, people first thought it was a nuclear attack. And here you can actually see how the dust trail looked like. You can actually, I don't know if you can hear the sonic booms. It was not nice. This is all caused by the fireball fragmentation. So the event itself had a yield of about 500 kilotons. So in comparison, that was way larger than the Hiroshima atom bomb. And it's about in the same range as the warheads that are mounted on the Trident II missiles. So this was a really, really powerful event. Though it's interesting, though, that its size was not that big. It was only 20 meters. But the peak brightness that it produced was about 30 times brighter than the sun. So magnitude minus 30, quite bright. The question was that was asked, people asked astronomers, well, why didn't we see this thing coming in? Well, very simply because it came from the sun direction, so we couldn't really observe in this direction. We usually observe asteroids in opposition, basically on the other side, in the Earth's shadow. And also in the last 10 years or so, the fireball wasn't really visible enough. It was pretty faint. Um, and the question is, how much damage can an asteroid of this size cause? And, should we be concerned? Well, here, what I have is what's called a kill curve. So basically, how many fatalities there would be for a given size of the asteroid. So when we get to about 1 kilometer range, we start seeing these global effects. So asteroids that are larger than 1 kilometer, we call them global killers. So basically, if something larger than 1 kilometer hits, that basically means the end of our civilization. Smaller than that, it's going to cause a very large number of fatalities. And actually, there's another limit that's been set at about 140 meters. If an asteroid of that size or larger hits, that would be an unprecedented disaster in human history. So basically, in the 1990s, NASA got a task from Congress that they should find 90% of all kilometer-sized asteroids, just to make sure that isn't something big coming to kill us all. And fortunately, most of them have been found, and in the next about 100 or so years, we are sure that we should be safe. On the other hand, the lower limit of about 140 meters, we're still working on that. So I can actually show you the current progress. Here we have the asteroid size, and we have the total number of them. So if we take a look at the 1 kilometer size, we can actually see that we have detected about, let's say, 90% of all asteroids, so we're kind of safe. But if we look at this 140 meter limit, we can see that we still have a ways to go. Again, these are the stats from 2014. Things have changed since then, but still we have ways to go. So where's Chelyabinsk, that big fireball that I showed you on the previous slides? Well, it's about here at 20 meters, and currently we've discovered way less than 1% of all of these asteroids. But there isn't really a big concern, actually, about these. So what does the future hold? So fortunately, in the next couple of years, there will be some big projects. There's going to be a satellite called NeoCam that's going to be launched, going to be searching for near-Earth asteroids, and there'll also be LSST, which was now renamed into the Vera Rubin Observatory, and they will try to fill this gap and try to find as many 140 plus meter asteroids, and hopefully in about 10 or 15 years we'll find about 90% of them. But these are just projections. So how often do these events occur? Well, if we take a look at the total fireball energy versus total number per year, we can see that Chelyabinsk type asteroids occur every 90 years or so. But what is the impact on the human population? So we actually had a student in our department, in our Meteor group, who did research about that, and she found that we should expect window breakage, considering that the population density stays the same on Earth as it is today, every about 5,000 years. So events like Chelyabinsk, where you have this big air blast over this heavily populated area, happens very, very rarely. So we shouldn't really be concerned about getting hit or even killed by an asteroid. But what about smaller stuff? What about that dust, millimeter-sized dust that I was telling you about? Well, that's another story. In 1993, there was a predicted meteor storm. So meteor storm is basically just a meteor shower that has a very high activity. So some of you might have observed the Perseids in August, and you know you have to kind of wait a couple of minutes until you see a meteor. Well, during a meteor storm, you would probably see about 1 meteor every second. It was just very, very high intensity meteor shower. So what happens then is a lot of these millimeter-sized particles entering the atmosphere at 20, 30, 50, 60 kilometers a second. their total spatial density increases, and also if you have a big satellite, well, the chance of a satellite being hit increases with the activity. So in 1993, there was a big communication satellite launched by the European Space Agency that got hit by a Perseid meteoroid during the Perseid storm, and it was rendered inoperable. Of course, satellite costing millions of dollars. You want to make sure that nothing happens to it. There was another case of X-ray observatory. Again, it's another European Space Agency satellite. They were observing into one source of meteoroids for several times, and they actually lost several CCD chips of their main camera. So this is the left picture is the before and the right picture is after. So you can actually see that they lost a big percentage of their instrument. Basically, probably no one really understood where the meteor sources are, and they shouldn't really be observing in that direction. And when you see projects like this, to me this looks like a really beautiful meteor impact detector. So if you hear that James Webb Space Telescope was, has been hit by meteoroids and the image is not as great, maybe try to remember this talk. So I just want to do a quick review about the current knowledge on meteoroids, just to show you, what are meteoroids, what is their composition, where are they coming from, and how many meteors do we actually see arriving every day to Earth. And I will also show you that some of these questions are kind of not 100% answered. So where are meteoroids coming from? So I showed you before that meteoroids can come from comets. And because of comet activity, but they can also come from asteroid breakups, asteroid collisions, asteroid fragmentation. We even see some active asteroids, which are probably comets, but their activity is so low, we call them asteroids. So what happens is that most of these objects are not in close proximity to Earth, but then due to some processes, they actually arrive closer to Earth, and we can see meteoroids coming from them. So let's say you have a comet whose orbit is a bit bigger than the Earth's, which is depicted here in blue, and a meteoroid is released from this comet. What happens then is one relativistic effect. It's called the Poynting-Robertson effect, which causes the meteoroid to spiral inward into the sun over a long period of time, several tens of thousands of years. But after a while, basically what happens is the meteoroid is breaking and its orbit is reducing. So after a while, it can actually hit Earth, and that's basically where we see meteoroids coming from. So sometimes we might not know, we might see a meteor shower, but we might not know its parent body. The parent body is basically the comet that it's coming from. One way you can study these objects is through interplanetary dust particles. So what are they? These are particles that are smaller than meteoroids. So we're talking about in the micrometer size range. In the 1950s, Fred Whipple, one famous astronomer, realized that the cross-sectional area and the total surface area of a spherical body decreases with the decreasing size. So what does that mean? So imagine you have a small meteoroid coming in, and it's just being heated by the air molecules impacting the front of the meteoroid. But because it rotates, it's being cooled on all sides. So bigger meteoroids, like millimeter size, centimeter size, they're completely disintegrate in the atmosphere, completely ablate away. But smaller dust particles on the micrometer size range, they actually don't get heated fast enough, and they can fall on Earth completely untouched. So the problem is, how do I collect these particles these dust particles that we know they come to Earth? How can you tell them apart from terrestrial dust, basically like our dirt? Well, it's a big problem. So that's why in the mid-70s, researchers started using U-2 spy planes to fly them really high and they used these dust collectors, and they would fly them many hours and just collect as much dust that's slowly seeping down the atmosphere, this interplanetary dust that's coming down. And they were actually able to find these particles and infer some properties and actually show that, yeah, we can actually tell them apart from Earth dust, and it's in line with certain expectations, et cetera, et cetera. One other way you can do it is you can actually go to Antarctica, which is a very clean place. It doesn't have a lot of dust, and these interplanetary dust particles, as they fall on the ground, they fall on the ice, they actually accumulate in certain areas, and you can collect them there and analyze them. Now, other way you can do it is you can just send a space probe to a comet, try to collect some dust and bring it back. And that's basically what the Stardust mission did in 2006. It collected only 1 milligram of samples. And the problem was the way they did the sample collection. So they flew the probe behind the comet, and the dust was coming in at very high velocity at 6 kilometers a second, not an hour, a second. And it hit this aerogel here. And you can imagine these particles decelerating very quickly in this aerogel, which is a couple of centimeters thick. And of course, when they brought it back to Earth, where you're observing there, try to measure, it's not the same as that particle that came in. Of course, it heated up. It was very heavily processed. And of course, you couldn't really analyze stuff with some carbon-based compounds because aerogel is basically just pure carbon. But things that they could find is the first amino acid was detected in these particles. And one other issue is that they collected very small particles, about 10 micrometers in size. And meteoroids are usually larger or around 1 millimeter, and they only got 1 millimeter size particle. So we don't really know, how a centimeter size meteoroid looks like. We still can't really very easily collect that sample. But we think it's some sort of a fluffy aggregate of small grains. But again, this is just a theory. There was another probe, the Hayabusa mission. They did a sample return from an asteroid. So asteroids, different from comets. Comets are these fluffy, comets are these objects that are very icy, full of these kind of fluffy, porous particles. Asteroids, on the other hand, you can imagine them as being like very rocky. And they collected about 1,500 particles, all of them very small, and they delivered them back to Earth. Some of you might know there's a Hayabusa 2 mission that's currently underway. It's visiting the asteroid Ryugu, and there's another almost identical NASA mission called the OSIRIS-REx, which is visiting another asteroid called Bennu, which looks about the same as asteroid Ryugu. It's just the Japanese did it sooner and for about 10 times less money. So where are meteorites coming from? Just a recap. So as I said before, you have meteorites coming from meteor showers ejected pretty recently, about in the last hundreds or thousands of years. And these are big meteor showers that you can observe: Perseids, Leonids, Orionids, Geminids, et cetera, et cetera. On the other hand, you have sporadics. So sporadics are meteors that came from comets, but they're so old that due to that, if you remember at the beginning how these meteoroids move when they're ejected from comets, their just movement has been so chaotic that you can't really tell from what comet they came from, and just kind of settled into the sporadic sources, which I'm going to show you later. And of course, perhaps there's some sort of an invisible source of meteoroids. And the thing is, there is a large dependency on how much light a meteor produces with speed. So very slow meteoroids, if they enter the atmosphere, they don't even produce enough light to be seen or observed by cameras. So it's very possible that there's a lot of dust that's coming in, very small dust that's coming into the atmosphere at a very low velocity, but we can't even see it. So there was a satellite called IRAS, which is it's called the Infrared Astronomical Satellite. And what it did, it took very detailed measurements in the infrared spectrum of the zodiacal cloud. So the zodiacal cloud is just this collection of dust in the solar system that you can even see before dawn, I think. So when people try to model what they see in the zodiacal cloud, try to reproduce the total brightness they could see in the structure of the zodiacal cloud, they had to include a lot of low velocity dust. So in this graph, in this solid line, you can see what this model is showing. So what is the velocity distribution and the relative number from the model. And on this graph here, so in this line here with this line, you can see what we observe. So this is from a radar and optical observations of meteors, and this is from the model. So you can obviously see a big discrepancy between the two. So we're not really sure what's going on. So what do we, what are we even observing? So how does the structure of meteor sources look like on the sky? So what you're seeing here is a graph that we usually like to describe as the Earth's windshield. So in the middle of the graph around here is the Earth's apex. So the apex is basically just the direction the Earth is traveling forward. So that's basically the forward direction. 90 degrees to the left around here is always the sun. So as you can always imagine, like this is, if this is pointing forward, 90 degrees to the left is always this line pointing towards the sun. And on the right is basically is this part here, which is the anti-sun direction. So as you can see, it seems that there are a lot of meteors coming from close to the sun, a lot of meteors coming from the opposite side of the sun, and a lot of meteors coming basically from this Earth direction. So you can imagine these as being kind of bugs. You know, when we're kind of driving through the solar system, we're just collecting a lot of bugs in our windshield. And of course, there are a lot of bugs that are hitting us from the front because we're, you know, driving into them. But there are also a lot of bugs that are hitting us from the sides. And these bugs, basically different meteoroids, are meteoroids in very eccentric orbits. So as you can see, this one, maybe on the second graph, you'll see these eccentric orbits. So basically, when it goes in, it will hit you from this sun side, and on the other hand, if it's coming from the direction from outside of further away from the sun, it will hit you from this anti-sun side. So these are the sporadic sources that we see in the solar system. But if I can go back to that slide, you can actually see, if I play this, you can actually see some of like a little bursts, like I think here and here. These are meteor showers. So basically just a dense area with meteoroids in the solar system that we hit, and we just see that as a meteor shower. So meteor showers are produced by centimeter to millimeter sized particles. As I said before, they do not evolve dynamically far from the parent body. So if you can measure the meteor's orbit and compare it to a comet's orbit, you'll see that it'll be quite similar. And the way we usually do that is we observe where the meteors are on the sky, we do the modeling, and we compare what are the predicted positions of those meteors. And if we compare the two, we can say, well, these meteors came from this comet. And there are actually a lot of meteor showers that don't have known parent bodies, / we don't know where they came from our comet. So as a final question, basically, how much meteors are coming to Earth? How many meteors are coming to Earth every day? And there are several measurements and several types of measurements you can do. One is the extraterrestrial estimate. What does that mean? Well, you fly a satellite and you see how many craters it has. And then from that, you can infer, how much stuff is coming down to Earth. The second type of analysis you can do is just observing meteors in the atmosphere using optical systems or radar and just seeing what is the flux of meteors coming down. And the third estimate is this ground accretion estimate, which is basically just analyzing the interplanetary dust particles that I was telling you about before. So basically, either from Antarctica or collection in the stratosphere using those U-2 spy planes and whatnot. So just to give you a short overview of how the extraterrestrial estimate is being measured. In 1984, they used a space shuttle to deploy LDEF, Long Duration Exposure Facility. And this was nothing but a big cylinder with many types of what were called targets. So there was one gold plate, and there was like a Kevlar plate, an aluminum plate. And then after 6 years, they recovered that, and the space shuttle brought it down, and they just counted the craters, and they used that to predict what is the flux of meteors coming down the atmosphere. Now, the problem here is the crater size is proportional to the total energy of impact. So if you want to tell, how many meteors are coming in each mass bin, what is the mass distribution of particles that are coming down? Well, that's kind of hard because you have to assume a velocity. The only energy that these particles have is the kinetic energy. If you want to, the energy, you measure that from the crater size, but you have to assume a velocity to get the mass distribution. So, what if the velocity distribution is wrong, then the mass distribution is wrong as well. So that's, you can see a problem with this kind of way of estimating the total number of meteors coming to Earth. And if we compare these estimates, you can actually see that they're not really that well. They don't really match that well. So, for extraterrestrial estimates from zodiacal cloud models, as I said, with that IRAS satellite, you could predict a huge number of 270 tons a day. With LDEF, it was about 110, but the uncertainty is huge. With in-atmosphere estimates, basically with meteor radars and optical radars, there's let's say about 40 or so tons a day. And if we look at those Antarctic ice cores and deep sea sediments where those interplanetary dust particles accumulate, you can also see there is a huge uncertainty on these numbers. So our recent best estimate, we think that about 40 or so 40 or so tons of extraterrestrial material arrives to Earth every day, but we're just not sure. So how do we answer some of these questions? How do we improve our current knowledge? Well, one way of doing it would be to install meteor cameras all around the world and observe meteors as best as you can. So the reason is you need this global network of observers because let's say you have a meteor shower that lasts very briefly for, let's say, an hour or two. So you can only observe it then in the part of the world where it was where the sun was under the horizon, because you can't observe meteors during the day. So if you only have, let's say, cameras, let's say, in this case in North America, and the shower outburst or the meteor storm or whatever happened during the night in Europe, well, you're out of luck, you can't see anything. Or, for example, even if you have your cameras concentrated all in Europe, maybe, it was cloudy in one part, so you have to have larger geographical distribution of these cameras. And what's also important is that you have to treat these cameras as a scientific instrument. It's not really a toy, because you're trying to measure all these things and make sure they're calibrated, make sure everything's fine, and then you're actually getting good data. So our answer to this is the Global Meteor Network. About 5 years ago, I met Dario Zubovic, and he was at the time a high school student who was very keen about meteors, very keen about Raspberry Pis, and he wanted to build a meteor camera connected to Raspberry Pi and just try to get something out of it, record something. And basically that is where this whole project started. The whole idea was that we want to use very cheap meteor cameras, very cheap computers, and we want to keep the cost of the whole system very low. And we want this system to be a fully automated meteor station, basically almost like plug and play. I'm going to plug it in, point it somewhere, and it's going to do it, the calibration, detection, data reduction, everything completely automatically. Because before that point, people were collecting a lot of meteor data, but it was a very, very painstaking process of manually reducing the data. And I remember I did several years of that, and I said, well, maybe it's better that I learn how to code and make the code work for me instead of me just slaving away and just reducing this data, which makes no sense. So that's basically what we did. So at this point, we have more than 200 cameras in about 20 or so countries. I'll tell you later about that. But first, I would like to talk about our hardware, and it's extremely simple. So we buy cameras with IMX291 or 307 or 385 sensors online, and these are reasonably cheap cameras. They give a video in HD resolution, 25 frames per second. They can even do 30, but that's not really that important. What's important is that the video that they give they're very sensitive cameras, and on one video frame, the limiting magnitude is about 6. If you have really good observing conditions, let's say somewhere up high in the mountains, it's even better than that. And we're using a Raspberry Pi for that. So basically what you're seeing here is more or less what the system actually is. The camera is directly connected into the Raspberry Pi, and the software is running on it and doing the processing and sending that to our server. So all software that we're using is completely open source. We have a GitHub page. You can download it and it'll run. We're still working on the documentation. That's the current goal of the project. And also what's very important is that we share all our data. So every orbit that is computed with these cameras shows up on our webpage about 24 hours after it's been observed. The data needs to be collected, processed, et cetera, et cetera. So this is just a high-level overview. How does the data actually look like? So this is one meteor detection from one camera in New Mexico, if I'm not mistaken. And you can see the meteor here, and you can see that it's actually quite sensitive. You can see the Milky Way and stars down to 6.5 magnitudes. But again, that depends on the observing conditions. We also detect bright fireballs, sometimes meteorite dropping fireballs, and we did observe several meteorite dropping fireballs with these cameras. And we have the expertise to reduce the data and direct people how to go and try to search for the meteorite. We also observed several meteor showers, and we have a lot of data on good meteor showers. We actually published a paper in collaboration with some folks at NASA who are interested in this stuff, and there are actually more papers in preparation. Besides meteors, we also see high atmospheric phenomena like sprites and elves. These are just basically this is just basically lightning that's not going from the cloud to the ground, but actually from the cloud up to possibly Van Allen belts, but we're not entirely sure. And what we make sure also is that our cameras are well calibrated. So we do an astrometric calibration once, and then the camera recalibrates its pointing every 10 seconds to make sure it's always pointing in the right direction. And as you can see here, the calibration is actually quite good, and it's completely automated. One thing that we noticed is that we have to do this automatic recalibration because the mount of the camera and the bracket expands thermally. Heats up during the day, cools down during the night, and it can actually move up to about 10 arc minutes throughout the night. The plate scale of our cameras is about 4 arc minutes per pixel. So basically, if you're not doing this recalibration, your camera will drift more than 2 pixels a night. It doesn't sound much, but when you're computing meteor trajectories, 2 pixels can translate to several hundreds of meters when trying to fit the trajectory instead of maybe 10 meters. One other thing that we're doing is we're also doing automated photometry calibration. So that what that means is that if you see something on the image, you can tell exactly how bright it is. You're trying to convert from the pixel brightness on the image to magnitudes. We're also doing automatic recalibration during the night. We have found we have to do that. We can't assume that the calibration doesn't change. Of course, the sky conditions are always changing. The transparency, cloud cover, even the moon elevation angle. So you can actually see here throughout the night how what you call the photometric offset is changing. So if you're not doing that, your measurements can be off by sometimes even more than the magnitude if you're not doing that calibration, and that's kind of important. Some products that our software produces. So every camera that's calibrated produces a graph similar to this every day, which basically shows you what meteor showers your camera observed last night. And as you can see here, this is from last year's Aquarids, which is around, I think, May last year. One camera observed a lot of these meteors, and you can actually see that our software computed the shower association, and you can see that a lot of meteors came from that one shower. So as I said before, all cameras send their data to our central server, and we run code on our server that computes trajectories and orbits, and that data is published, and everyone can access that within, let's say, 24 hours if the code works as it should. The current status of the network, I honestly didn't have the time to update this map. We have actually many more cameras than this. This was from February this year. So as you can see, we have a lot of cameras in New Mexico, I think around 30-ish. We have some cameras in California, some cameras in the East Coast around the Washington area, a bunch of cameras here in Ontario, a bunch of cameras in Croatia, some cameras in Germany, Netherlands, Belgium, a lot in the UK, France, some in Spain. We have 2 cameras in the Canary Islands, very, very beautiful dark night sky there. We have some cameras in Russia. We're actually very happy with these cameras here because they have some remarkable clear weather here all the time. And I think a couple of cameras in China. And we are seeking to expand, especially to the Southern Hemisphere. We have some folks in Brazil currently deploying cameras and trying to send the data. So when we have these observations from individual stations, how do we compute meteor trajectories? Well, it's actually quite simple. You basically just triangulate the position of the meteor in 3D space, and then you're just trying to estimate its initial position and its direction where it came from and the initial velocity. Once you have that, you just kind of take that, what we call the state vector, and just shoot it back into space, and you compute the meteor's orbit. And of course, if you can do that for many meteors, you can really get a good sense of where they're coming from in the solar system, what their parent bodies are. By that I mean from what comet they came from, et cetera, et cetera. One other thing that we are measuring is the photometry, basically the light curves of meteors. As you can see here, the meteor ramps up, goes up, it peaks here, and then goes down. So what you can do from this is you can compute the initial mass of the meteoroid. And the way you can do that is, I'd just like to briefly explain how it works. I think it could be understandable. So the only energy that a meteoroid has when it's entering the atmosphere is kinetic. It has no other source of energy. It's not exploding, that's some sort of chemical process like dynamite or whatever. No, it's just entering and it's just expanding its kinetic energy. And it's converting a portion of that to light. So we know what the equation for kinetic energy is. And if you can account for all this energy, and you know the velocity, because you measured it in the trajectory, you can invert it you can invert the mass. The way you can measure this energy here, well, you just sum up all of this energy that was expanded for the light curve. We just integrate all of that, and just assume that there's some sort of a conversion factor from the kinetic energy to light, which called luminous efficiency, it's about 0.7%, although it's kind of quite uncertain. And you also have to assume what is the power of that meteor there, which is about 1,000 watts. And using that, you just integrate the light curve, assume some sort of a luminous efficiency and the power, and you can compute the meteoroid's mass. That's why we're making sure that our photometry calibration is good and correct. Once you have those things in hand, so you measure the position of the meteor, you can measure the velocity really well, and then you can measure the deceleration really well, and the light curve. What you can do is you can take a meteoroid ablation model, which is just a bunch of like differential equations to describe how meteors ablate and fragment, et cetera, et cetera. And if you can fit them to your observations, then you can infer some properties of that meteoroid, what its initial mass, velocity, and bulk density. Bulk density is very important because that's one parameter we don't really know. It's really hard to measure. As I said before, no one really has like a centimeter sized meteoroid. No one really collected it before. And one way to do it is to observe meteors with these cameras and fit these models and try to derive that from the models. So what is our data so far? We've collected about 100,000 orbits to date, but we're looking into expanding that, expanding the reliability of our system and expanding the documentation, make sure everyone understands how the system works, and of course, improving the data collection and even the sensitivity of our cameras. So what are we looking for at this moment? Well, the model that we found that it works best is that there is an advanced amateur in the community which understands how the system works, how to build these cameras, and then finds people in the local amateur community to be hosts for these cameras. So what happens then is that someone in the network, which is mostly me now because I'm doing most of the code development and support, just supports the camera, the local contact, and that local contact supports the hosts of the cameras locally, and sometimes if needed, I can support the hosts directly. And I was fortunate enough to find a couple of guys in Croatia who are willing to build these cameras for people who want to buy ready-made cameras, and they sell them for about, I think, 500 euros a system, which is about 500 bucks for people who don't want to assemble them and want to buy them as a complete system. So I think that's about all I have. So thank you for your attention, and just if you have any questions, I'm here. And I think before we might have like a short maybe question session, and then we should move over to the folks in New Mexico who might want to say about their experiences with the system, and then we might want to have another question section. I don't know, whatever you guys want to do.
Oh, Denis, that was really very interesting. You have a number of people over here who are interested in participating. So what's the process that they might go to, and how dark is the sky?
Eric,
Yeah.
I'm going to suggest that we ask questions about the information so far that we've been given. I think Peter and Bob are later going to be telling us about the things you're about to ask.
Okay.
I may be wrong, but I think they're going to be telling us about that. And so let's start with any questions that are related to what did who was it, John or Ray said he was like drinking from a fire hose, all that meteor stuff coming at him. And eh, what questions might people have about the presentation itself? And one of them that was right early, remember when you showed the pretty graph of the comets breaking up and
Yep.
making meteor streams? It was a Vimeo video, I think. What was the software you used to generate that? Do you know? That was a particularly,
You mean this one?
I think that's what we meant.
Okay, yeah. So this is work by Rachel Soja. She works at the European Space Agency, and she uses her own code integrators to generate this. So this is, the type of code you just can't go and download online. This is someone like a scientist writing their own integrators and their own visualizer, and they don't really. Yeah, this is not like a user-friendly code. People who
Okay.
write this stuff, it's like
But
science.
for
Yep.
those of us who want to act like we know about meteors and want to show this off to other people in our club, we
Yep.
can go get the Vimeo, and there's the
Yep.
the
The whole
URL.
video is there. Yep, the whole video is
Okay.
there.
I don't know if that answers the whole question, Were there any other questions related to the presentation itself? Let me get over there real quick.
No, I didn't see any, but people are
Okay. Then
interested in finding out more
the big
about.
one is how do we get to play? How do we get to play?
Yes.
Peter, do you want to talk, or Bob, or what's happening next?
Yeah, I'm going to stop presenting. There you go. Yeah, I think it would be great if Bob or Pete would say a couple of words about their experiences. So just to give you some background, a couple of years ago, Pete Eschman bought our first prototype camera and installed it in New Mexico, and very quickly the network spread from there, and I think they have a network of about 30 or so cameras. So it'd be great if they could tell about their experiences with the system, and yeah. So go ahead.
Yeah, this is Bob. Pete is going to cover this for us, Pete and Steve. So I'm going to, if you'll unmute yourself, Pete, and you got it.
Pete, we can't hear you. You have to unmute yourself.
At the bottom of the screen, there's a little microphone.
Peter, we are seeing a screen that says, "Why should I want to record meteors?" We aren't hearing your voice yet. You need to pull your cursor down to the bottom of the screen. You got it? That you?
This is Steve, actually, and
Okay.
I was going to just.
Okay. You're going to do the audio over his screen share.
That's right.
Is that it?
And
Okay, go for it.
I'm going to just read this slide, which I know is bad form, but we have a lot of questions that will probably come up from it. Why do you want to do this? And Pete's and my opinion has always been that citizen science is important, and this is the chance to get involved in citizen science at a very, very basic and valuable level. You can get involved at any level you want to. You can get to cooperate with others. You can see cool meteors, night-long time-lapse movies, and other excellent and really fascinating images. Is something that your camera produces every night and that you can look at. You can share your results with folks in your club or observing group, or post them to your own website. And then what we did is, Pete is actually the person who did all the work here, but I helped him a bit here and there, is you get several club or group members together, put up several cameras in an area, spread them out a little bit so that they can get good triangulation, and you can have gossip sessions and talking how to do this, or you can also build cameras. We built cameras we built our own cameras, which is another thing that you can do, save a little money, and also you get really intimately involved with the Raspberry Pi and the cameras and all this stuff, and you get really, really great data out of it. And so we've had a great time, and basically we've had a lot of fun doing this, and we've gotten a lot of people in our area, in our club, interested in it, and we're covering a good part of the state now, with Meteor cameras. So let's see. I don't know if Pete wants to. I'm not looking at the camera. Let's see here. Let's get back to the presentation.
Okay. All right. Can you folks see that screen okay still?
Yeah.
We see the screen, but there's nothing on it right now.
Gotcha. Okay. Let me try to get back to what I was sharing then. My apologies. There we go. Okay. Yeah. Okay. So basically, this is kind of a sales pitch. And I will say, maybe you need a little Raspberry Pi in your life. They can be a great way to get started with Linux or programming using the latest languages. The Raspberry Pi is really an amazing platform for education. all you need to multi-purpose your RMS Meteor camera hardware is a spare keyboard, monitor, and mouse, or for less than $100, you can purchase a dedicated set of hardware for keyboard, mouse, and HDMI monitor. Once you got all that, you can also use your Meteor Station's Raspberry Pi 4 during the day when it's not busy. Actually, the Pi 4 has plenty of power to spare, and you may find that you can use it even possibly when it's recording data. We're still evaluating the Pi 4s. They're a lot more powerful than what we started out with, the 3 pluses. Within our local area, this is sort of the 3,000 kilometer view elevation of our, what we call the New Mexico Meteor Array. And as I try to keep tabs on 23 or so stations in our array, it sometimes feels like herding cats. I volunteer as sort of a regional coordinator, and I interface with Bob Massey, who's starting up a similar effort in California. We found that we need to kind of split up the workload. We have a guy by the name of Steve Kaufman, who runs US 0006 and 0N. And he's been able to take advantage of some software hooks left by Denis that allow us to run a custom script at the end of every data processing. And we've used that to extend automatic data backup of summary data to our server here in New Mexico, also managed by Mr. Kaufman. And we've also added error checking that helps us keep track of any stations that might be malfunctioning. And for some stations, we've got them configured so they automatically upload a little bit of SURMA data and graphics to the user's website. Another one of our members, Gene Morose, who runs 0L, has assisted in running a wide variety of statistical analyses on our data. He runs data summaries through UFO Orbit software, which matches up stations that record the same meteor. And Gene's work has helped us to refine the station pointing to improve a statistically valid coverage over as large an area as possible. Gene has it to the point now where the spatial distribution of meteors observed within a 100 by 100 kilometer box centered on the interstate I-25 and I-40 intersection meets the statistical test for being plausibly a completely spatially random distribution. So this suggests there are no major gaps in our coverage. And then other members have tried to develop expertise in things like making system plate par files that improve the data reduction of the individual stations, working on documentation, evaluating hardware issues and enhancements, monitoring data collection, and providing technical expertise on the Linux operating system, which helps because that's the underlying operating system on the Raspberry Pi. So in summary then, I try to send out emails periodically to our group telling us about the status of our New Mexico Meteor Array. And more recently, we've turned to Zoom meetings to bring folks together. Because in some cases, our folks are many miles apart. I think there's a span from Santa Fe to Quemado to Edgewood, probably on the order of 200 miles between some of our stations. So in conclusion, our New Mexico Meteor Array is truly a group effort. And I'll leave it at that. You can see the bang for your buck. It's hard to get all this stuff for the price point with any other set of hardware. And you get to create great citizen science.
Thank you, Pete. One thing I'd like to say is that a lot of people will be, would want a system now and to install it, and it would naturally contact me. The problem is I don't have a lot of time, but we have very excellent groups.io group, and people there will be able to help you. And if you don't have a lot of like DIY experience, it might be a bit challenging, but you'll get there. If you want to buy a kit or a system that's complete, there exists a company in Croatia that sells them, but now because of the the global pandemic and whatnot, they're pretty backed up. So you might not get to install this thing immediately, but it'll take some time. Just as a heads up. And the whole effort is just concentrated around a few people, and we might not be able to handle the response. That's why we want to organize local networks that are self-supporting.
Is there a place we can get a parts list?
Yep. So every person who wants to build one, they should actually send us an email, and we kind of cater a parts list for them. Because sometimes it might be confusing. There's a lot of stuff on the parts list, and we usually try to select the optimal lens for the local light pollution conditions, et cetera, et cetera.
And how do we get a hold of you to do this?
So there is a groups.io mailing list. So if you just Google Global Meteor Network, and there's a website, and you can go on the website, and there's a contact form. There's the link to the mailing list, the link to the code, the link to the data. Everything is there.
What kind of
By the way,
Skype?
the link is on the bottom of the video.
Yeah,
Dennis,
we
what kind of Skype do you need in order to be able to set up one of these stations?
We need to ask if Bob Massey wants to share anything to what I've already said.
Bob?
I would just add, and Dennis pointed this out, they're looking for stations everywhere. And so this everything you've heard here is pretty much North American based physically, but certainly, as Dennis said, we're looking for stations all over the world. We just updated the wiki as well. So a lot of the information and the steps you need to take and about the putting the cameras together and so forth are on it's not perfect, but it's over on the wiki as well. And that wiki again is located on globalmeteornetwork.org.
Yeah, we're actually looking for people who are willing to contribute to the documentation, and willing to maybe at the beginning build a system by themselves, understand how it's all put together, and then go back and change the wiki, contribute to the docs, and make sure everyone can do this. I would love to do that. I don't have the time though. Sorry, Alex, I can't.
Your mic is muted.
Yeah, I got it. I have one of these on my house, and somebody asked if you need good light pollution and stuff. Yeah, I got as good a light pollution as anybody. There's like 13 million people living between me and the beach, and it's only 50 miles and 50 miles away. So yeah, I live in Moreno Valley, California, which is just next to Riverside, San Bernardino, and we're within an hour of Los Angeles, so we've got plenty of light pollution. And I do generate data that I've been told is useful. They can use it to track meteors and things like that. I should tell you that I was brought into this by Bob. Bob owns the observatory that's 2 down from mine over at GMARS, and he saw a sucker when he knew it when he saw it, and he says, "Hey, how would you like to get involved in all this other stuff?" And I said, "No, because I don't want to have to learn all this stuff. I don't want to do anything. I'm not smart enough to handle all that whatever weird stuff you're doing over on that Raspberry Pi." And he says, "Oh, come on, all you got to do is put this on your roof, and the Raspberry Pi will take care of it." That wasn't exactly true, but it was pretty close. It wasn't horribly far off, with the assistance of Peter mostly, I think, and Denis also, and some other people. They walked me through the technical parts of it, and it was a while before I got everything pointed right and everything. But basically, it was a couple of trips up the ladder and got it going. And now every once in a while, I go to my tight VNC and I say, "Hey, up in the attic, Raspberry Pi, what are you doing up there?" And it says, "Oh, I'm taking pictures of meteors and compiling data and sending it off." Now, Peter now Dennis rather told you a bunch of stuff about, oh, and you can get this data and that data and that data, and then you can compute this and that. Yeah, you can, but you don't have to. You can just look at the pretty pictures of all the meteors that came streaking by your sky last night, and that's kind of fun to do. So it can be done. It costs $400 or $500 to just do it store bought, and it costs some energy and to figure it out yourself. But it can be done, and even a guy like me that really doesn't understand this stuff. I've never worked. What is that? Linux in the Raspberry Pi. I'd never worked with it before, and I've looked at GIMP back when I was poor and couldn't afford processing software, but I never used it because it was all geeky. And that's the stuff that is in Pi in the Raspberry Pi. But I don't really need it all that much. I can still look at my pretty pictures of the meteors going over my house, and I know that my stuff's being reported back to Denis and the rest of the global meteor network, where no comet will go unfound and untracked someday. So, are there other questions out there, Eric?
No, I think people are just trying to absorb this and see how they might become part of the system.
Okay, and basically getting part of the system means going over to the globalnetwork.org, is it? And what is that? Is that right? And starting from there. It's not as developed as, you don't just write them a check and here it is. You're going to have to do some work, and that's why they're looking for people that might want to be group coordinators on a local level, like Peter is. Peter does not want to set up the United States network of meteor watchers, but he's real happy working with the group in New Mexico who do a great job, and they meet every once in a while by video and stuff like that, and go over stuff. But he doesn't want to do that for everybody, and he shouldn't have to do that for everybody. But it would be nice to have a few people spread throughout the country that could talk to their astronomy clubs and talk a few people into $300-400 worth of investment if you do it yourself, and you can be tracking meteors, and someday you'll be cited in a research journal.
Yeah,
That's
one thing I could comment is that I've actually got 3 cameras on my house pointed in 3 different directions. And for the most part, each of our cameras, the current hardware and lens we're using, we get about, Dennis, what, about 88 by 44 degrees field of view, I think.
That's about right.
Yeah. And then what I'm seeing here, I'm very close to the Albuquerque Sunport Airport here in Albuquerque. And so I got lots of planes flying over. And I have to say that the software does a really good job of ignoring planes. And it does a pretty darn good job of ignoring satellites as well. So hats off to Denis for the type of detection software that he's created here, because it really does a pretty fine job. Sometimes you'll get an image of a meteor, you go, well, why is there a plane in that image? And it's because you look closely, there's a faint meteor that showed up the same time the plane was in the field. So anyway, it's a lot of fun.
We have a couple of technical questions over here. First off, Steve has pointed out that he was going to try to produce a picture so you can see what it is, or URL so you could link on that and go see what the kinds of pictures you get. Let's see, is there any thought to using the image generated as a seeing monitor? Can that be done?
Yep, it can be done. So our code is open source and it's extendable. So if you want to write your own scripts that want to do whatever, it can be done. And we actually have people writing their own customizing scripts. And there was this one guy from the Netherlands, if I'm not mistaken, who used our software as a base for his satellite tracking code. So that's well, we're trying to, the whole project is open source for a reason, because we want people to support the project. If I made this project closed source, that means that everything that people want that needs to be done, I would have to do it. And I just like, no, at some point, I want this project to be self-sustaining, and that will happen at some point.
John has asked whether the finished setup, once it's set up and running,
Mhm.
is it high maintenance or low? And that depends, I guess, on your pigeon population. Um, you might have to go up there every now and then and clean something up, but no, as Steve has answered here, it's medium and it's getting better all the time. Speaking only for myself, I set it up in early January or so. And then I went away for a month and I came back and found out that it wasn't doing the job it was supposed to do because I hadn't done some things right. And so I got up on the ladder and adjusted it a little bit. And then I haven't really thought about it in probably 6 weeks. Okay. Can either Steve or Peter or Dennis tell us, or Bob, tell us what happens what happens in a typical night with the camera? What does the camera do? In particular, every morning, you tell us about the process. It grabs the pictures, it sorts them out, it processes them, it picks out the meteors. I know all that stuff. But why am I saying this when we've got people who actually know? And the flow of data out each morning after local processing. His question is about the magnitude has been a problem at our very rural site with the limited internet bandwidth.
Mhm.
Okay, so maybe we can't deal with that, but tell us what all happens in any given night.
Sure. Yeah, if you don't mind, I'm going to say a few words, and Pete, if you want to continue. So, the daily operations is basically about half an hour after sundown. Recording starts, the sky gets dark enough, and images are collected. At the same time, the detection is run. Meteors are detected, and then sometimes the detection might go on after sunrise until the processing catches up. That might go on for a couple of hours later. But with the new Raspberry Pi 4s, they're so fast that it's done within half an hour of dawn. And after that, the data gets processed a bit more. All meteor detections are archived and uploaded to the server. And the size of the archive really varies. We still have some issues with fast clouds during the nights of the full moon, and that can be an issue. We're actually working on a machine learning solution that's going to look at all meteor detections and say, oh, is this really a meteor or is this a false detection? That's actually something that's been done in the past, and we're trying to filter out all meteor detections that we have and just upload to the server real meteor detections. And some data products that you can see on your Raspberry Pi is that meteor shower association graph that I showed you before, and those calibration files. But as for maintenance, things have really improved with the Raspberry Pi, which allowed us to use some new versions of software libraries. The Raspberry Pi 3, at some point, it's kind of been not really that stable, but with the 4, we actually have much more success. I think that's basically all that I have to say. So Pete, if you don't mind, just
Sure. Let me indicate that the typical graphics that we upload for 000G, which is at the General Nathan Twining Observatory, the Albuquerque Astronomical Society's observatory, we upload the stack file that shows an overlay of all the detections on one frame. We upload the radiance plot, which you saw an example of in the slideshow. And we also create a time lapse that is a sample of every cap of the contents of the night-long capture. And that can be very interesting to watch. Sometimes you see the flashes of the meteors, you see planes go over. At one point I saw this great streak, and then I saw this really odd expanding area. And I suddenly realized, well, that's a jet contrail is what that is. And so there's a lot of really nice graphics that that are created. I will say regarding a slow network connection, the Pi only really needs a network connection to upload the data to Denis's server and to be able to download. This is an important consideration. It was on one of the slides, is that every morning when these stations boot, they do an update, a software update, and they pull down any new code that Denis or anybody else has contributed. So your software is always up to date. But we've got some slow network connections in rural areas. And yeah, the Pi takes a while to upload in the morning, but it's usually not a problem.
Dennis, does the setup, or can it be programmed and take advantage of if you have an observatory, if the roof is open or not open, or it's a cloudy night or it's a clear night? You're muted.
Sorry, a detection algorithm takes care of that. It actually detects stars in every image. And if it can see some stars, then it will run the detection algorithm. So you might actually use use it in a different way. You know, you might want to use that as a cloud detector. It can be done if you want, right? Just use the byproducts of the Pi and use that as an input to your observatory and whatnot. Now, one thing that I wanted to show is we actually do have a status web page that can be enabled for every system. So if you don't mind, I can just share my screen again. That's great.
Yeah, the Insta stream would be a good place.
Can you see my screen now, or?
Yes.
Excellent. So we have so the guys in Croatia who are selling these cameras are also hosting this website. And here on the website, I opened the status web log for one camera in the Canary Islands, which is actually quite nice. The elevation there is like 2,500 meters. And you can see the stack of all detections, all meteor detections last night. And you can also see a stack of all files. You can actually see star trails here, planes and whatnot. We have these little thumbnails of all pictures taken throughout the night, and you can actually see the moon here. It's in the middle of the field of view, and that's where detection efficiency drops significantly because it almost just saturates the whole field of view. And of course, you can see Dawn here. The meteor shower association graph, you can see the Meteoroids were active last night. You can also, let me see, go back. There's some calibration graphs here. So here's the astrometry calibration, photometry calibration. Again, you know, it's just for meteor nerds. You can definitely see how the photometric offset changed significantly once the moon entered the field of view. And at the end, we also have the time lapse. So you can click on that. I think I can just put this, and it just gets uploaded to YouTube, and you can just see the stars appearing. The quality is not great, I think, because of the YouTube compression algorithm. It just doesn't, it decides not to show the video in full quality unless enough people watch the video or something like that. You can see Starlink. We see Starlink many, many times.
Yes, we've had Starlink bombarding us,
Yep.
the new constellation. And sometimes, even if it's somewhat cloudy, that watching the clouds roll through overhead is very mesmerizing. It's these time lapses are a lot of fun.
That's the moon. And yeah, that's about it when it comes to the weblog. And the data is available on the globalmeteornetwork.org website. And here's just this windshield graph that I was showing you. Again, we have some Meteoroids, but again, this is just, you know, some stats for meteor nerds. And you can see the data in the last month. You can see again the Meteoroids. Last month we had the Lyrids, and basically everything is here. If you want to access individual like orbits and whatnot, just click on this, and you'll just get this huge table here that you can load into Excel, whatever, and do some analysis. Again, for people who want to do this. I think that's basically about it from my end.
Yeah, and one thing I can comment on is that because the data is summarized in a form you can dump into a spreadsheet, it's in common formats shared by a number of systems, and you can put your data straight into a free software called UFO Orbit that will allow you and your local network of folks to see all of the orbital calculations, the trajectories, and the ground plots of the data that you've collected locally for any observation that matches from more than one station. It's really a lot of fun to play with that. And, there's nothing keeping you from doing it. That's what our guy Gene Morose does, is he uses UFO Orbit to basically refine down all of the matches we're getting in our network.
Yep. Just excellent. One thing that I also want to say is that, as you probably noticed, we don't really deploy a lot of all-sky cameras. We notice that they are not that useful. I understand when people think about Meteor cameras, they're like, oh, I want to install an all-sky camera, sees everything. But it turns out that big fireballs are quite rare, and you might want to have to wait several years before you actually see like a meteorite dropper or a big fireball. So what we prefer to do is install these cameras that are much more sensitive, and they see many more meteors a night compared to an all-sky camera. So we get a lot of questions about that, and we prefer these moderate field of view. We're talking about 90 times 40 degrees field of view, and it's actually, from the practical standpoint, you don't have to sometimes go up to the roof, and sometimes you might have some trees around and whatnot, and you will always find at least 90 degrees somewhere we can kind of fit in your camera, and has no obstructions in the field of view.
Yeah, and I think you indicated at one point, if you really wanted to use these lenses and these cameras to create an all-sky coverage, it takes about 5 cameras, I believe,
Yes.
to accomplish that.
Yeah, so we actually have a system like that here. These camera numbers from the weblog from CA5 to 9 and 11 to 15 are 2 systems like that. Basically, like it's an all-sky system. It's like a fly's eye, I guess, type of system where you have 5 cameras pointing in every direction, and that's how you get the all-sky coverage. And the cost of that system is probably similar if you want to buy like one high-end all-sky camera, and this is much better because of like the resolution that you're getting and the number of meteors that you're seeing.
Peter and Dennis and everybody else that is associated with Bob, Steve, what's it like being as Ray, astrophotography, wants to know, what's it like being a citizen scientist? What am I actually going to do? What am I going to get out of it as far as science and everything else like that goes?
Well, I guess I could try to answer that. As I said, we're collecting data every night. We can share the data with our other nearby stations, and you can actually share the common observations. You get an automatic data reduction that shows you the altitude and azimuth, RA and DEC of the beginning and ending of the trail, the altitude at which it begins and the altitude at which it ends. So every morning you can look at your data and go, oh, I got a magnitude 4 object here, and it came in at 110 kilometers and disappeared at 80 kilometers. And so you can take as much interest as you like in the data that you're collecting.
Is the data usable by professional scientists trying to do their work? Do they ever incorporate the work of the global meteor network in their own work?
Well, I joke that you think you own these cameras, but really Denis gets the data. That's my joke.
I just want to point out that we have used the Global Meteor Network data set and published a paper very recently about measuring dispersions of meteor showers with some collaborators, with some NASA collaborators. It's actually people who fund most of the work I do professionally. And in the future, we're actually planning to publish another paper using this data. And all the people who contributed to the project are acknowledged in the paper. so the data is useful both, let's say, from the amateur perspective and from the professional perspective. And one big aspect of the project that we're trying to push is the educational aspect. So, when I started, there was nothing even close to this. And we want to make sure that other young students are introduced to science through meteor astronomy, because it's actually a nice way of doing it. And especially through an open source project, if they know a little bit of programming, they might get involved. And we actually have a couple of students that approached us and deployed these systems, and they're using that as their maybe a school project or something like that, which is really cool.
One of our members is very interested in getting cameras in some of the high schools near where he lives in the western part of New Mexico, because this would be a really good way to get younger kids, high school students, maybe even middle school, involved with doing their own science. And they can always buy a Raspberry Pi to play with on their own too. They sell for 35 to 50 bucks for your very own computer, and then you just have at it, learning as much Python as you like.
Yeah, it could be a good, science fair project. It's like, I measured the heights of meteors with my Meteor camera, the brightness of meteors, whatever, meteor showers. You just put it on a poster and, win an award.
I can answer that also from a slightly different way, is that if you're asking what do you need to do as the citizen science test, you may not, once you've got that thing installed and up and running and delivering its data, remember all the data is going up to Denis and other professional astronomers all over the place. And it's basically, the Pi takes care of it all. Every once in a while, you should check to see whether the Pi is still operating, but you can really get by without doing much at all if you're not interested in being the active scientist. So if you just want to contribute to the project, you can put one of these on your roof. And another point I wish to make is that I think it was Eric that asked, does your observatory know to open up and so that it exposes it? No, this thing is sitting outside your house. This thing is sitting up on your roof in a waterproof housing, and it just sits up there. It doesn't need an observatory or anything else like that. My neighbor, who's a very sweet man, was very concerned that my security camera was pointing to the sky. And he wondered how I could ever catch burglars and robbers with my security camera pointing to the sky. And I told him, well, Gene, it's not really for robbers and burglars, it's for meteors. And it's a meteor camera pointing right up to the sky. That's all it is. Okay, so I had some questions about all sky cameras. I think what you guys have to realize is that this is kind of a package, and you might have some parts around that can kind of work and stuff like that, and you can jury rig them so that they do work pretty well together. But it's kind of calibrated to produce data with given cameras at given resolutions and things like that. And the software is made to work all together. So you kind of have to buy into the system a little bit. All right. It's not just point a camera up there and start contributing data. I see that we have some questions coming in now. I'm not sure we're going to be able to answer all the technical questions, but remember, we have given you a few links today. If you've got any questions, please get them on into us, and we are going to try to get them in. Let's see. Denis, what's the data that you collect? Will it help save the world? Denis, Ray wants to know, will your data help save the world?
It's funny, the closest thing you can come to a Superman these days is you probably join to become an astronomer, and become an asteroid hunter. When it comes to meteors, we're not trying to save the world. We're trying to save astronauts in orbit, satellites, equipment like that, and just want to make sure that our expansion into the, beyond is safe. There's some concern now with asteroid mining that might produce artificial meteoroid streams coming from asteroids. So imagine so the thing is, all asteroids that you want to access are those with what's called the low delta V. So basically you have to spend a little energy to come to those asteroids. So you start mining, and of course, a lot of these like particles just start popping out. And because the velocity difference between the asteroid and the Earth is so small, that means that these particles can come to Earth. So we want to make sure that the debris environment around the Earth is quite clean. So what happens if you have, like the Wild West in outer space, when everyone's just mining asteroids, producing a lot of this dust, this stuff comes crashing down on satellites and astronauts in orbit and God knows what, right? So it's basically, we are here to monitor, see if something's going on. We have the data, and we can say, okay, we can make some executive decisions because we know what is going on. That's basically the whole point of the project, is to have constant monitoring. If you think maybe like, oh, like there's got to be someone, who's monitoring everything, they know everything. It's like, well, actually, no.
The Planetarium de San Felician says that it might be good if these things could produce real live images. They don't really produce live images, right? They wouldn't be good for an outreach type of thing.
Yeah, so it's actually possible. The IP cameras that we're using, you can connect them to your router, and what you can do is just say to Pi, like, oh, just take the feed from this camera. But what you can do then is just open the stream in another browser or whatever, and just show that on a different screen. So that's one possible configuration. I don't prefer it, because what happens sometimes is that the router might cause some delay between the camera and the Pi, and then there might be some lost frames. But if you really want to do it, it's possible.
As I understand it, if we're having problem uploading one day because our internet is down, the data still stays on the Pi, right? And next time it gets a chance, it sends it up.
Yep.
Yeah.
So
Magdalena Observatory or Astronomical Society was worried about whether they can get that connection. Well, you may not have a good connection, but all it's got to do is sit there and transport the data up. So,
theoretically, you could have a Pi sitting out in the woods with no network connection at all and a solar panel to power it. And you could hike to the Pi once a month, grab the data, take it back to town and upload it. Now,
okay.
Theoretically, that's doable. The Pi can store quite a bit of data and keep it safe for well beyond a month.
Okay, I think we're running out of Tim's made some suggestions that we could hit up some STEM schools. What we need most of all in this is some people spread throughout the country, throughout the world, because we do have a worldwide audience that can, kind of get together with their astro buddies and somehow make it a point to get some of these pods going. Get them, get a couple of cameras every 50 miles until we can cover the whole sky. So, and by the way, I think we gotta start calling here. So I don't see any more questions. I think we really appreciate your participation. So, all the guys that have contributed to this, Steve and Peter and Bob and Dennis, we really want to thank you for being here on the Astro Imaging channel. Next week we've got observatory building going on. Manny's going to come in and show us how to build an observatory. We've had about 75 85 people watching all night, and we'll have probably another 600 to 1,000 watch in the course of the next week usually. Remember, you can go to the globalmeteornetwork.com and get information. Hit those things. Also, remember to go ahead and subscribe to this YouTube channel. The more people we get subscribing, the more we can reach out to everybody. And I think we've got some technical questions, but I think some of those technical questions can be better put to the guys on the Global Meteor Network directly. So I'm going to call it. Toga, we ready?
Yeah, I'm ready. Whenever you guys.
Bye, everybody. See you next week.